Welcome to the Crazy Hat Chemist. So another video here on thermochemistry. So let's get moving. Bam! So today we're talking about a generic heating curve. You should see that there's a graph right here, and it is temperature versus constant heat. Okay? All right, so all of these look like this. They could be compounds, they could be elements. I'm going to give a specific example with water since that is the most frequently used one. However, it could be for aluminum. It could be for ethanol. It could be for butane. It could be for anything you want it to be. It's a generic heating curve, and all these will apply except for the specific numbers that I give for water itself. That's H2O. Okay? All right, so this first flat line section of this, the first horizontal section of this is going to be the melting point. The second flat line horizontal section of this graph is the boiling point. Notice that the melting point and the freezing point are the same temperature. Depends on which direction you're coming from. And the boiling point and the condensation point are the same temperature depending on which direction you're coming from. Now, for water, the melting point or the freezing point is 0 degrees Celsius. And the boiling point or condensation point is 100 degrees Celsius. So those 2 points define the graph. So no matter what graph you're looking at, you definitely need both the melting point and the boiling point to get these 2 temperature values to set up the entire graph. Okay? That's very critical. That's your first step. Okay? Then the next thing here is that this is an idealized graph, and that the real version of this graph is really smoothed out on the whole graph and the curve, right? I have lines that are strict up and then over and then up and over and up and over. Now, it doesn't quite look like that in reality. It's much smoother, but the purpose of this is so that you get the idea of what's going on. So that first sloped section, that's the lowest sloped section, is a solid, and that's obviously below the melting point. The next sloped section is between the melting point and the boiling point, and that is a liquid. Now, beyond the boiling point, the final slope section is in the gaseous state. So I got 3 states of matter: solid, liquid, gas. The solid is at the lower temperature, the gas is at the higher temperature, obviously. And what defines them is the melting point and the boiling point, which defines these 3 different states of matter of the same either element or compound. Okay. Now, the in-between section, that is in between a solid and a liquid, where the melting point is a solid and a liquid. That means that on this horizontal, on the first horizontal section, you actually have an equilibrium between the solid and the liquid state throughout this entire line, except for the 2 points on either end. Okay? And I'm going to get more into that as we do some of the math problems. The second horizontal section at the boiling point is where you have the liquid state and the gas state in an equilibrium together. That means both the liquid and the gas state are there together at the same time. And it's the interconversion between the liquid and the gas, or the gas and the liquid, depending on which direction you're going. Whether you're going from the bottom to the top or from the top to the bottom on this graph. Okay? All right, hopefully you got that part so far. Okay, now the math that we're going to be using here is that in the solid section, we're going to be doing Q equals mc for ice, the specific heat capacity for ice, times the change in temperature. Notice that it is a sloped section, so you do have to be using a change in temperature. Okay, the next section here that has a sloped section is the Q equals mc, C for the liquid, times the delta T. So it's the mc delta T, but the C, the heat capacity for the liquid state. Okay, and then the gaseous state, you got Q equals mc for the gaseous state, heat capacity for the gaseous state, times the change in temperature. Remember, all of these sections, the solid, the liquid, the gas, all have a change in temperature because it's a sloped section. You should see from the far left-hand side where the y-axis is, it is a change in temperature if you go up or down here. Now, in the first horizontal flat section here, where you have the interconversion between the solid and the liquid, you have Q equals mc, the heat of fusion. The heat of fusion is your constant that you're using. Now notice, since it's a horizontal section, there is no change in temperature. Okay? That is, this is all occurring at the melting freezing point at this horizontal section. So that's why there's no temperature term within this section. Okay, the next horizontal section is Q equals mc. Okay, except for the C, the constant in this section is the heat of vaporization, because you are going from the liquid to the gaseous state, or the heat of condensation, the opposite direction, as a cooling process, or cooling it rather. Okay, so Q equals mc, heat of vaporization. So these are the 5 steps that we have. So we're going to label these 5 steps. Okay, we got step number 1. Okay, we got step number 2, we got step number 3, we got step number 4, and we got step number 5. So each of these 5 different steps, we're using similar but yet different equations, and each step is a different constant. Okay, so where are you going to be able to find these constants? Within your textbook, or in the appendix, or the Handbook of Chemistry and Physics. That's the CRC. So I'm going to give you the constants here for water. So for water, here are the constants. Now I'm going to start at the bottom of this where it says step 1. The specific heat capacity for ice, the Cp for ice, is 37.8 joules per mole Kelvin. Notice that there's a temperature term in this constant. That's because there is a change in temperature at step number 1. Step number 2, there is no change in temperature. It's a complete horizontal line, and that's why this constant, the heat of fusion, at 6.01 kilojoules per mole, has no temperature term in it. Step number 3 also is a sloped section of this graph, and it does have a temperature change, and that's why there are units of temperature in it. And this is the specific heat capacity for water, for liquid water that is, and that's 4.184 joules per gram Kelvin. Step number 5 has the heat of vaporization at 40.7 kilojoules per mole. Again, this step number 4 is a flat section of this graph. It's a horizontal section. There is no temperature change, and therefore there are no temperature units in it. Step number 5, the final last one up at the top, specific heat capacity of steam, Cp for steam, is 36.5 joules per mole Kelvin. Again, that one has a temperature unit in it because there is a temperature change here. I want you to look at some of these values, and the heat of vaporization compared to the heat of fusion. The heat of vaporization is a very large number at 40.7 kilojoules per mole. That's why steam is so hurtful to you. Okay, now there's one number that you should have memorized, and that's 4.184 joules per gram Kelvin. You can actually transfer this into degrees Celsius for all these temperatures, because the temperature, when you're doing a change in temperature, the units, the interval for Kelvin and degrees Celsius is actually the same. So you can actually use the same one there. Okay, I am the Crazy Hat Chemist, and I got a crazy hat. Don't be a turkey. Give me a thumbs up. Don't be a turkey. Subscribe to my YouTube channel, and don't be a turkey. Look me up online and find my website with all the great worksheets and so many more videos. I'll see you next time for more cool chemistry videos. Bye for now.